Welcome to the second lecture of differential geometry. In this lecture, we will try to cover up the remaining half of the syllabus. But before starting our new topic, we shall first rectify some mistakes that we had committed in the previous lecture. The first mistake was here. When we substitute this point 1, 2, 2 in our vector fx, fy, fz here, then we get the value 2, 4, 4. But we had mistakenly written 1, 4, 4 there. Now that is rectified, and so we replace this 1 by 2 here and then compute the determinant, and we get the value 8i minus 2j minus 2k. So our vector for finding the equation of the tangent is a comma b comma c, which is 8 minus 2 minus 2. Now substituting these values in the equation of a tangent, we obtain the equation of tangent like this. And the second mistake that had happened in the previous lecture, it was at time 45 minutes, and the mistake was our given r of t is t square t cube, and here we are trying to find the equation of a tangent at this point x naught, y naught, z naught with coordinates t square t cube. So we have to replace this first row of this determinant by x minus t, that is x minus x naught, second by y minus y naught, and y naught is equal to t square, and z minus z naught is equal to t cube. But we had mistakenly written t here and also t here. Now using this substitution and then equating this determinant to 0 and computing the determinant, we obtain this equation. The answer is correct. There was no problem with the answer. And finally, we had asked this question here that you would have practiced yourself, but the answer here is x minus y plus z plus t equal to 0. But instead of t here, I had written 1 in place of this t. Now the main concern of the present lecture is to study the surfaces. So we start with the surfaces. We define what we mean by a surface. A parametric surface is a smooth map which we denote by r of uv, defined as x of uv as its first coordinate, y of uv the second coordinate, and z of uv as the third coordinate, where this uv is a vector in r square, where r is a function, where r is also actually a vector valued function. It's a function from some subset d of r square into r cube. So this is how we denote a parametric representation of a surface. Now here we take some notations that we will frequently use when studying surfaces. Now as we have the equation of a surface as r of uv is equal to x of uv, y of uv, comma z of uv, we have the derivatives of this r, like we denote the first derivative by r1, which we denote by del r by del u, which is equal to del x by del u, del y by del u, del z by del u. And similarly r2, which is the first derivative of r with respect to the second independent variable v, so this will be del x by del v, del y by del v, del z by del v. Similarly, the second order derivatives, now r11, this will be equal to del square r by del u square. Now r12, which is equal to del square r by del u del v. Similarly r22, which is equal to del square r divided by del v square. Now since our map is smooth here, so we will have this r12 same as r21. Now we take our first definition here regarding the surfaces. This is a point, suppose P on a surface S is called a singular point if this R1 cross R2 is equal to 0, and a point where R1 cross R2 is not equal to 0 is called a regular point. Now let's take up some examples of the surfaces. We take the first one as r of uv, which is equal to r sine u cos v, r sine u sine v, r cos u, which is actually a sphere centered at origin having radius r. If we put r equal to 1, then we will get the unit sphere. And second is we will take another representation of a unit sphere, which is a little bit unusual. This is 2u divided by 1 plus u square plus v square the second coordinate is 2v divided by 1 plus u square plus v square, and the third coordinate is 1 minus u square minus v square divided by 1 plus u square plus v square. So this is a unit sphere centered at origin. The third one is ellipsoid, whose equation is given by r of uv is equal to a sine u cos v, b sine u sine v, and c cos u. And we can also express this in the implicit form like x square by a square plus y square by b square plus z square by c square is equal to 1. We also call this equation, which is in the implicit form of the ellipsoid, we can also call this as the constant equation of the ellipsoid in parametric form. Similarly, we have the other surfaces. I shall just mention the names of them, like hyperboloid of one sheet, similarly hyperboloid of two sheets, then elliptic hyperboloid, similarly hyperbolic paraboloid, similarly torus. Here I just recommend that we must be knowing the equations of these some fundamental surfaces. Now, as we can see here in the first and the second, if we put in the first equation of the parametric representation of a surface, if we put r equal to 1, then we get the parametric equation of a sphere, parametric representation of a sphere. And second, this is also a parametric representation of a sphere, and these two representations are different. So therefore we have one result here. Parametric representation is not unique. So therefore, given one parametric representation of a sphere, we can transform that into another parametric representation by some transformation. And if suppose we have u is equal to phi of u dash v dash is suppose a transformation of the parameter u into new variables u dash v dash, and similarly v is transformed by a function psi of u dash v dash is a transformation of parameters, then we call this transformation as proper if Jacobian of pi and psi, if Jacobian of this pi comma psi is not equal to 0. And by Jacobian we mean a 2 cross 2 determinant whose first row is the derivative of pi with respect to u dash and v dash, and derivative second row is the derivative of psi with respect to u dash and v dash. Now equation of tangent and normal to a surface. Now here we shall mention the equation of tangent and normal to a surface in both the cases when the equation of the surface is given in parametric form, as well as when the equation of the surface is given in the implicit form or in the form of a constant equation. If we have r of uv is equal to x of uv, y of uv, z of uv is a surface, then the equation of tangent at any point, say x, y, z, is given by r minus r dot r1 cross r2 is equal to 0. And we can easily understand this since we have the vector r1 and r2, which are both tangents to a surface at a particular point, and these are the tangent lines, and then this r1 cross r2 is a vector which is perpendicular to both r1 and r2. So therefore the dot product of r minus r with a vector which is perpendicular to both the tangents will give us the equation of a tangent at any point x, y, z. This is actually the scalar triple product, which we can also express as, or we can write this as the scalar triple product r minus r, then r1, r2. This is equal to 0. Or we can also express this in terms of the Cartesian coordinates like x minus x, y minus y, z minus z. Then here in the first row of r1 we can write del x by del u, del y by del u, del z by del u, and similarly the third row will be the derivative of r with respect to v, that is del x by del v, del y by del v, del z by del v. The determinant this is equal to 0 gives us the equation of tangent at any point x, y, z. And that is one case when the equation of a surface is given in the parametric form. The second case is if the surface is given by f of x, y, z equal to 0. Then the equation of tangent is x minus x into del f by del x plus y minus y into del f by del y plus z minus z into del f by del z is equal to 0. And this is the equation of a tangent at any point x, y, z. Now we can come to define the equation of a normal. Equation of normal is given by x minus x divided by del f by del x is equal to y minus y divided by del f by del y, which we can write as fy, and equal to z minus z divided by fz. While fx, fy, fz represent the partial derivatives of f with respect to x, y, z, which we can also write as del f by del x, del f by del y, del f by del z, and this is the equation of normal at any point x, y, z. So therefore, in order to write down the equation of a normal, we just have to find the direction cosines of a normal, which are given by del f by del x, del f by del y, del f by del z at any point x, y, z. Then just write x minus x by fx, y minus y by fy equal to z minus z by fz. But sometimes the question may just be asked to find the direction cosines. In that case, we will use this equation, which is normal vector to a surface. This is given by n, which is defined as r1 cross r2. Now if it is three coordinates are n, x, n, y, and z, then these are the direction cosines of a normal vector to the surface, and in this case we can write down the equation of a normal as x minus x by nx equal to y minus y by ny equal to z minus z divided by nz. Or equation of normal is given by r minus r is equal to, suppose, some lambda dot n for t for this lambda belonging to r. This is also a way to write down the equation of a normal to a vector. This is also a way to write down the equation of a normal to a surface, r minus r equal to lambda dot n, where n is the vector given by r1 cross r2. Now let's take an example to evaluate the equation of a tangent and normal to a surface. Find the equation of the tangent and normal to the surface, which is given by x of uv, y of uv, z of uv is equal to u, v, u square minus v square at any point u, v equal to 1 comma minus 1. So in the solution, what we have to do, first we immediately write how do we write down the equation of a tangent. Equation of a tangent is written as the scalar triple product of r minus r, r1 and r2 equal to 0. So therefore we immediately evaluate what is r1 and r2. Now here r1 is equal to del x by del u, del y by del u, del z by del u. So this is equal to del x by del u is 1, del y by del u is 0, and del z by del u is 2u, which is equal to 1, 0, 2 at the point 1 comma minus 1. Similarly, r2, which we define as del x by del v, del y by del v, del z by del v. Now taking the derivative, this gives us 0, 1, minus 2v. So this is equal to 0, 1, 2 at 1 minus 1. So the equation of tangent is determinant of x minus, we can now write this as, suppose, x naught, y minus y naught, z minus z naught. Now the second row of this determinant is 1, 0, 2, and the third row is 0, 1, 2, and equated to 0. Now here our question is how to evaluate this x naught, y naught, and z naught. Now if we look at the given equation, we have x of uv equal to u, so x is just equal to u, so x naught can be put equal to 1. And similarly y of uv equal to v, so therefore y is equal to v, that means v is equal to minus 1, so y is equal to minus 1, that is y naught equal to minus 1. And similarly z is equal to u square minus v square, which is 1 square minus 1 square, that is equal to 0. So where y naught z naught. This can be defined as x naught is equal to, now suppose we can call it as u naught, y naught is equal to suppose v naught, and z naught is equal to u naught square minus v naught square. Now substituting the value 1 minus 1 for u and v, we get 1 minus 1 0. Now substituting this value of 1 minus 1 0 in this determinant, we obtain the equation of tangent is, so the equation of tangent is 2x plus 2y minus z is equal to 0. So this is the equation of a tangent that we obtain by evaluating the value of this determinant. Now the equation of normal is given by x minus x naught divided by the direction ratio, suppose let's call that as we have called that as nx, y minus y naught divided by ny is equal to z minus z naught divided by nz. Now here we first evaluate the normal vector is n is equal to r1 cross r2. Now this is equal to the determinant I, j, k. Now r1 has its value 1, 0, 2 and r2 is 0, 1, 2. And evaluating this, we get 2i plus 2j minus k. So thus the direction ratios of the normal vector are 2, 2, minus 1. Hence the direction ratios of the normal are 2, 2, minus 1. So the equation of normal is x minus 1 divided by 2 is equal to y plus 1 divided by 2 is equal to z minus 0 divided by minus 1. Now if we look at our given equation, it was given in the parametric form u, v, u square minus v square. We can express this equation in the implicit form also. Now this is another way, another method to find the equation of tangent. If we first write down our given equation in the implicit form, so our r of u v here in this case is u, v, u square minus v square. We can express which can be written in the implicit form as x square minus y square is equal to z. And now here we will find the equation of tangent. So we find equation of tangent and normal at, now u, v is equal to 1 minus 1, so x, y, z will be equal to 1 minus 1, 0, which is already computed. Now here we can use the equation of a tangent that was given in the implicit form. So the equation of tangent is x minus x naught, now fx, plus y minus y naught fy plus z minus z naught fz is equal to 0. Now substituting the values, we get x minus 1 into fx, that is equal to 2x, plus y plus 1 into fy, that's equal to minus 2y, plus z minus 0 into fz, that is equal to minus 1, because we can shift this z onto the left hand side to write down the equation of f of x by z. So actually here we have f of x, y, z is equal to x square minus y square minus z. So this gives, now substituting the value of x, y, z as 1, minus 1 and 0, we get 2 y, then again plus 2 into y plus 1, then minus z is equal to 0, or this gives plus 2y minus z. Now here we get minus 2, here we get plus 2, this is equal to 0. So this again the same equation of a tangent that we had obtained in the previous case. So this is 2x plus 2y minus z, and here we also obtain the same equation, 2x plus 2y minus z. And similarly we can find the equation by normal by just using x minus 1 divided by fx, y plus 1 by fy, z minus 0 by fz. Now we write one exercise here. Find the equation of tangent and normal to the surface x by z is equal to 3 at minus 1, minus 1, 3. And one point that we must always remember here is when we are asked this equation of tangent and normal to a surface at some given point, first of all, we must verify whether this point lies on the surface or not. If we look at this point minus 1, minus 1, 3, if we substitute here in this equation x, y, z equal to 3, it will satisfy this equation, so this point necessarily lies on the surface. But if we are asked to find the equation by tangent and normal to a surface, assuming at a point, suppose 0, 1, 2. Now as this point 0, 1, 2 does not lie on the surface, so there is no point of finding the equation of tangent or a normal at this point. And in this case, when we are given an MCQ, then we will just find out the option which writes none of the above, and that will be our answer. Now let's take up another example. Find the unit normal to the surface x square y plus x square y plus 2xz minus 4 equal to 0 at 2, minus 2, 3. Now as we are asked to find the unit normal to the surface at this point, first of all in the exam we will verify whether this point lies on the surface or not. If it does not lie on the surface, then our answer to the question will be none of the above, or else the question will be a false question. Now let us follow this. First we directly write the direction ratio of normal are del f by del x, del f by del y, del f by del z, where this f is equal to x square y plus 2xz minus 4. So this gives 2xy plus 2z, x square, 2x, which are the three partial derivatives of f with respect to x, y, and z. Now substituting the point, we get the answer as minus 2, 4, 4. This is at the point 2, minus 2, 3. Therefore, we have to find the, now as we are asked to find the unit normal, hence the unit normal has the direction ratios which are minus 1 by 3, 2 by 3, 2 by 3, which we can easily compute by taking the vector and dividing it by its length. So the equation of the unit vector is x minus 2 divided by minus 1 by 3 is equal to y plus 2 divided by 2 by 3 is equal to z minus 3 divided by 2 by 3. Now we come to our next topic, that's envelope of 1 and 2 parameter family of surfaces. Now here first of all we write down the notation. The notation f of x, y, z, a equal to 0. This is a 1 parameter family of surfaces. 1 parameter family. And similarly f of x, y, z, a comma b equal to 0. This is a family of surface with 2 parameters. 2 parameter family of surfaces. Now by its envelope we mean a surface that is tangent to each member of the family at some point. Now how do we find that family that is tangent to each member of the family at some point? The envelope to 1 parameter family of surfaces. To 1 parameter family of surfaces is obtained by eliminating a from f equal to 0 and del f by del a equal to 0. And similarly the envelope of 2 parameter family is obtained by eliminating a and b from f equal to 0, del f by del a equal to 0, and the third equation del f by del b is equal to 0. And the easiest way to do is it like this. We solve this del f by del a and find the value of a in terms of x, y, z, and substitute the value of a in the given equation to eliminate this a. And similarly from this del f by del a equal to 0, del f by del b equal to 0, we find the value of a and b in terms of x, y, z, and substitute that in the given equation f equal to 0 to get the family of 1 parameter family of surface or 2 parameter family of surfaces. Now here we take one exercise that we shall solve quickly. The exercise is x square minus a square x plus b square minus 2bxy is equal to z. So find its envelope. So what we do in the solution, we write f is equal to x square minus a square x plus b square minus 2bxy minus z. So then we call this is equal to 0. Now del f by del a, this is equal to minus 2ax is equal to 0, and similarly del f by del b, this is equal to 2b minus 2xy is equal to 0. So therefore here we get this a is equal to 0, and from here we get b is equal to xy. Now using these two values in the given equation, then given equation, or we can call f, reduces to, now as a is equal to 0, so we get x square minus a square x, that is 0, plus x square y square minus 2 x square y square is equal to z, which gives x square into 1 minus y square is equal to z is the required envelope. Similarly, we can find the envelope of one parameter family of surfaces. Now let's take up the first and the second fundamental formulas, which are defined in terms of the first and the second order fundamental magnitudes. So we begin it like this: if we have R is equal to R of UV is a smooth parameterization of a surface, then we can define the direction vector. Then this dr, which we call the direction vector, this is defined as r1 du plus r2 dv, where r1 represents the first order derivative of r with respect to u, and r2 represents the first order partial derivative of v r with respect to v. Now if we take the norm of this vector, so then we get this norm of dr whole square. This is equal to dot product of this dr with itself, that is r1 du plus r2 dv. It is dot product with r1 du plus r2 dv. Now simplifying this equation, this becomes r1 dot r1 into du square plus twice r1 dot r2 du dv plus r2 dot r2 into dv square. And this is then expressed in the form of the scalars e du square plus twice f du dv plus g dv square, where this e is defined as r1 dot r1, f is defined as r1 dot r2, and g is defined as r2 dot r2. So therefore this e, f, g are scalars, which we call the first order fundamental magnitudes, and this equation e du square plus twice f du dv plus g dv square, this is called the first order fundamental form, or the first fundamental form. So this e, f, g, we call them first order fundamental magnitudes. This first fundamental formula, this captures the intrinsic geometry of the surface, like it captures the length, or it can capture the distance between the points, or it can capture the angles that the tangents or the normals form on a curve. This first fundamental form is usually denoted by, most of the time it is denoted by I, but here we shall deliberately write it as m1, which is now defined as e du square plus twice f du dv plus g dv square. But most of the times on the books this is denoted by I, and the second fundamental form is denoted by double I. This can be put in the matrix form, or we can say it can be put in the quadratic form, which can be written as this m1 is equal to du dv, which is a row vector. Now multiply it with the matrix E, F, F, G into the matrix vector du dv. Now here this matrix, which is the matrix of this quadratic form, this is known as the metric tensor. We mentioned one theorem regarding this first fundamental form. The metric E du square plus twice f du dv plus g dv square is a positive definite quadratic form, and is invariant under a proper transformation of parameters. Now before taking any examples, we shall first come to the second fundamental form. The second fundamental form is similarly defined as, we shall directly denote it by m2. This is equal to L du square plus twice m du dv plus n dv square, where now L is defined as this R11 dot n, where this n is a unit vector which is perpendicular to the surface at a point, and similarly m, this is equal to R12 dot the unit vector n, unit normal vector, and n is defined as R22 dot n, where n is the unit normal vector. Now again these numbers L, m and n, they are the scalars because they are defined as a dot product of two vectors. R11, as we already know, it's the second derivative of r with respect to u. R12 is second derivative of r with respect to u comma v, and R22 is the second derivative of r with respect to v. Now the second fundamental form can also be expressed in the quadratic form like this: du, or we can write this m2 is equal to du dv. Now with the matrix m n, sorry, this is lmn, L m m n multiplied with this du dv. So this is the second fundamental form in the matrix form. Now before proceeding further, we shall take an example to compute these first and second order fundamental magnitudes for a given surface. Let's consider an example. Find the first and second order and the second order fundamental magnitudes, or the first and the second order fundamental magnitudes for r of uv equal to u cos v, u sin v, 2v square. Now the solution is, we know that this r1 is defined as del r by del u, which is equal to cos v sin v 0. R2 is equal to del r by del v, which is equal to minus u sin v, u cos v 4v, and R11, which is del square r by del u square. So this is the second derivative of r1, or the first derivative of r1. Now cos v has derivative 0, sin v has derivative cos v, sorry, sin v has derivative again 0, and third is again 0. And similarly r12, this is equal to minus sin v cos v 0, and r12 is the derivative of r1 with respect to v, or the derivative of r2 with respect to u. And finally r22 is equal to minus u cos v minus u sin v comma 4. Therefore we can evaluate E. Therefore our first order fundamental magnitude E is equal to r1 dot r1, which we can write as modulus of r1 whole square, and r1 is equal to cos v sin v 0, so cos square v plus sin square v plus 0 square is equal to 1. Then f, which is equal to r1 dot r2. Now this is equal to, similarly we can compute this is equal to 0, and then g, which we define as r2 dot r2, which can be expressed as modulus of r2 whole square. Now r2 has the coordinates u sin v, u cos v, 4v, and this becomes u square plus 16 v square. So these are the first order fundamental magnitudes. Now for the second order fundamental magnitudes, we need to evaluate the unit vector. So now the unit vector n is r1 cross r2 divided by the length of this unit vector, that is modulus of r1 cross r2. Now this is equal to 1 divided by modulus of r1 cross r2 into determinant of I, j, k. Now in the second row we will take the coordinates of r1, which are cos v sin v0, cos v sin v0, and in the third we take the coordinates of r2, which are minus u sin v, u cos v, 4v. Now evaluating this, we arrive this unit vector to be equal to 1 divided by u square plus 16 v square. Now the first coordinate of this r1 cross r2 is 4v sin v minus 4v cos v, and here we have u. We can look here, we have obtained this u square plus 16v square, and modulus of r1 cross r2 also has u square plus 16v square, but this is just a chance of happening. This is not always true. We can have different values for g as well as this r1 cross r2. Therefore we can calculate, therefore our L is equal to r11 dot this unit vector n. This is now equal to 0 because our r11 is equal to 0. And similarly m, which is equal to r12 dot the unit vector, this becomes equal to minus sin v. Next m is equal to r12 dot the unit vector n. This is equal to now r12, that is equal to minus sin v cos v 0, then dot this unit vector, which is equal to 4v sin v minus 4v cos v and u, and divided by 1 divided by u square plus 16 v square. Now taking this dot product, we finally arrive at minus 4v divided by u square plus 16 v square. And similarly we can define n as r22 dot the unit vector n. Now calculating this one also, we get 4u divided by u square plus 16v square, and the details are left as exercises. So therefore we can write down the first and the second fundamental forms. Thus the first fundamental form is m1, which is equal to e du square plus twice f du dv plus g dv square. So this is equal to du square because e is equal to 1. Now f is equal to 0, and the next term is plus u square plus 16 v square dv square. And similarly the second fundamental form is m2, which we write as l du square plus twice m du dv plus n dv square. Now substituting the values, we get L is now 0 here, and m is equal to this minus 4v, so this becomes minus 8v divided by u square plus 16v square du dv plus 4u divided by u square plus 16v square dv square. So these are the first and the second order fundamental magnitudes. Now we also leave one exercise here. This is for a sphere. R of uv is equal to sin u cos v, sin u sin v, cos u. Find the first and the second fundamental forms. Find the first, that is m1 and m2. And here I shall mention the answers, just like in this way, to verify whether it is done correctly or not. We will get this m1 is equal to minus m2. In the case of the unit sphere, the first fundamental form is just the negative of the second fundamental form. Right, now we define another definition, the shape operator. the shape operator, this is a matrix defined like this S, which is defined as M1 inverse into M2. Now, as we have already discussed it previously, that this matrix M1 is a positive definite quadratic form, so it is always invertible. Therefore, we can find out this inverse M1 inverse into M2, and this operator is called the shape operator. The eigenvalues of this operator have a nice names. The eigenvalues of S, which are denoted by K A, K B, are known as principal curvatures. So this is one easy way of defining the principal curvatures. They are defined as the two eigenvalues of the shape operator S, which is defined as M1 inverse into M2. Now, in terms of these principal curvatures, we can define the Gaussian curvature is defined as the determinant of this shape operator, which is also in terms of the fundamental magnitudes like ln minus m square divided by eg minus f square. And this also now the determinant of the shape operator will be the product of the eigenvalues, that's Ka into Kb. And similarly, we can define the mean curvature, which is defined as 1 divided by 2 into trace of this shape operator S, which is now equal to 1 divided by 2 this Ka plus Kb. So it is the sum of eigenvalues divided by 2, and we know the trace of a matrix is the sum of the eigenvalues, and this also has its form in the first and the second order fundamental magnitudes, that is, it is equal to, now we do write it like this, E, now we write F here and G, now write L, M, N, now put 2 here, minus here and plus here, and denominator is 2 times Eg minus F square. So this is how we define the Gaussian curvature and the mean curvature in terms of the shape operator and the first order and the second order fundamental magnitudes. Now here we shall not discuss an exercise in detail, but we shall quickly put up the results, and the details will be left again as an exercise. So consider a vector, consider a surface R of uv is equal to sine u cos v, sine u sine v, and cos u. Then this E is equal to 1, F is equal to 0, and G becomes sine square u, and similarly L is equal to minus 1, M is equal to 0, N is equal to minus sine square u. And this is also asked in the previous exercises to find the first and the second fundamental formulas of this unit sphere, and now here we have written all the values for this E, F, G and L, M, N. So we just need to substitute these values in the formulas for M and N, M1 or M2 to get the first and the second order fundamental magnitudes. But now here we are interested in evaluating this Gaussian curvature and the mean curvature. So then this Gaussian curvature, which is usually denoted by K, which we can write as Ln minus M divided by Eg minus F square. This is equal to now L into N, that is equal to sine square u. M is equal to 0, so in the numerator we get sine square u divided by now E into G, that is equal to sine square u, and F is equal to 0, so this is equal to 1. Therefore, for the unit sphere, the Gaussian curvature is equal to 1. And similarly, the mean curvature is, which we write as 1 divided by 2 Ka plus Kb, which is equal to 0 in this case. And we can write down this where we have this 1 divided by Ka plus Kb, it is defined as En minus 2 Fm plus Gl. Now substituting the values of En 2 Fm minus Gl, we get the numerator as sine square u minus sine square u. And the denominator is non-zero, so this is equal to 0. We can take another example. So this is another question. Find the Gaussian curvature and the mean curvature for R of uv is equal to u cos v, u sin v, 2v square. which is the question for which we had evaluated the first and the second fundamental forms. So we have all the values of E, F, G and LMN. Therefore, we can immediately write down the first Gaussian and the mean curvature. So in the solution, we have this K is equal to Ln minus M square divided by Eg square. Now using the values as obtained in the previous exercise, we get this minus 16 V square divided by U square plus 16 V square whole cube. And similarly, the mean curvature is equal to 4U divided by 2 times U square plus 16 V square whole square. So these are the Gaussian curvatures and the mean curvatures of this surface at any point U and V. Now let's take a Weingarten equations. Weingarten equations gives us the derivatives of the unit normal with respect to U and V in terms of the first order fundamental magnitudes and the first order derivatives of the tangent vectors. So these are two equations which we need to remember them. This is given as minus 1 divided by h square into this matrix R1, R2 into M1 inverse into M2. This is equal to N1, N2, where we shall define these notations N1, N2 later on. And this is also equal to, or we can also write this as 1 divided by h square into this M minus L, N minus M, which we can better write in this way. We can write like this L, M, M, N, and then put minus here. Then multiply this with the matrix with the first order fundamental magnitudes, write E, F, F, G, and write minus for these two, and multiply this as a row vector R1, R2. This is also equal to N1, N2. Now here we have these new notations H and N1, N2, where N1 is equal to del N divided by del U, and N2 is equal to del N divided by del U. So these Weingarten equations therefore provide us the values of the first order partial derivatives of the unit vector with respect to U and V in terms of the first and the second order fundamental magnitudes, and using the first derivatives of the tangent vector at that point. And moreover, and this h square is also equal to Ln minus M square. In fact, we have, sorry, this is not h square. This is the value for t square. So this is t square, and h square is the sitting dot notation defined for Eg minus f square. So these are also two different notations used in differential geometry everywhere, that h square is equal to Eg minus f square and t square equal to Ln minus M square. Now let's define the normal curvature. Normal curvature. This is defined as the curvature of the normal section. And a normal section of a surface at a point is obtained by intersecting a surface with a plane that contains the normal vector of the surface. So if a plane contains a normal to the surface, then the section drawn by that plane with the surface is called a normal section. And then the curvature of this normal section is called the normal curvature. This normal curvature is denoted by Kn. This is defined as L du square plus twice M du dv plus N dv square, whole divided by E du square plus twice F du dv plus G dv square. So this is the normal curvature in the direction dr. So this is in the direction dr, which is defined as du comma dv. Now if we are given some fixed direction, then we can accordingly substitute the values of du and dv in this equation to find the normal curvature in that direction. Now we have another theorem for this normal curvature, which we call the Meusnier's theorem, or this is also sometimes written as Meusnier's theorem. This gives us the normal curvature in terms of the curvature of the surface and an angle theta, where this angle theta is the angle between the principal normal vector of the curve and the surface normal vector at that point. Now here this Kn, we know it is a normal curvature. It is a notation for a normal curvature. And now this K is the curvature of the curve. Curvature of the curve lying on the surface. And then this theta. This is the angle between the principal normal of the curve and the surface normal at that point. So this is Mann-Nier's theorem, which gives us the principal curvature in terms of the curvature of the curve and the angle theta, which is the angle between the principal normal vector of the curve and the surface normal vector of that at that point. Now let's evaluate the principal normal curvature for this paraboloid. So we take an example. So find Kn for x square plus y square is equal to z, which is actually a paraboloid. And we find it as a curvature at 0, 0, 0 at the origin. So in the solution, what we have to do, we have to find this first and the second order fundamental magnitudes. So we are given our uv, which we can express as u, v, then z is equal to u square plus v square. So x equal to u, y equal to v, z equal to u square plus v square. And let the direction be, d is equal to cos alpha sin alpha. So we are asked to find the curvature of this paraboloid at the origin in the direction of cos alpha sin alpha, where alpha is some scalar. Then at 0, 0, 0 at the origin, we have this E is equal to 1, F is equal to 0, G is also equal to 1, L is equal to 2, M is equal to 0, N is also equal to 2. I have deliberately left solving this E, F, G, L, M, N, and they are also left as exercise. So then this normal curvature Kn, which is equal to L du square plus twice M du dv plus N dv square, whole divided by E du square plus twice F du dv plus G dv square. Now here this du and dv is cos alpha and sin alpha, so du is cos alpha and dv is sin alpha, and this finally becomes 2. Now when we substitute du is equal to cos alpha, so this becomes cos square alpha here, m is equal to 0, and n sin square alpha here. So we take, but L and n, they are both equal to 2, so we can take 2 common from here. The middle term is 0, so sin square alpha plus cos square alpha is 1, so the numerator is 2, and similarly the denominator is equal to 1. Now we mentioned some results here. This is in fact one kind of a definition. This is an equation. The equation giving the principal direction is we have actually always two principal directions, and the equation that gives these principal directions at any point is given by em minus fl into du square plus en minus gl into du dv plus fn minus gm into dv square is equal to 0. But now, as we can clearly see, this is difficult to remember, but this can also be presented like this, which can be written as, first we write dv square, then minus du dv to keep the positive sign in the middle, and then du square here equal to 0. Now write E, F, G, L, M, N. This determinant is the equation giving the principal directions. Now next, if we write, so we have this notation, denote P by this em minus fl, and by 2q we denote this en minus gl, and by r we denote fn minus gm. Then the condition that the two principal directions are orthogonal, is, now this is in terms of this PQR and EFG, and here we mention an easy way to remember it. We have to write this equation as, first we write E, then we write F, then we write G. Then in the reverse order we write P, Q, R, then put 2 here, minus here, plus here equal to 0. So this is the condition under which we can call the two principal directions to be orthogonal to each other. Now we have another definition. A point on a surface is called umbilic if this E equal to F equal to G divided by L, M, N. If these two ratios or three ratios are equal, then we call the point an umbilical point. Now finally, we have one important result regarding when a surface point is called elliptic, hyperbolic, or parabolic. A point on a surface is said to be the first one This is said to be elliptic if it is Gaussian curvature, k is less than 0. Sorry, if it is Gaussian curvature, k is greater than 0. That is, now we know the Gaussian curvature is given as ln minus m square divided by Eg minus f square. If this is greater than 0, then the point on that surface is called an elliptic point. And second is said to be hyperbolic if this k, which is defined as ln minus m square divided by Eg minus f square, if this is less than 0. And the third one is, this is said to be parabolic if the Gaussian curvature. Now we also know the Gaussian curvature is the product of these two curvatures, principal curvatures k and kb. This is equal to ln minus m square divided by Eg minus f square. If this is equal to 0, then we call the point to be parabolic. Now let's take one example for this one also. For the surface z is equal to x square plus y square, which we have taken earlier, and we call it a paraboloid. Then we have this Gaussian curvature, which is defined as ln minus m square divided by Eg minus f square. This is equal to 4, which is greater than 0. Thus, this is actually at the point 0, 0. Thus, 0, 0 is an elliptic point for a paraboloid centered at origin. Now let's take up another topic, the developable surfaces. We write its definition. Developable surface is a surface that can be flattened onto a plane, without distortion. So therefore, actually, it is a surface whose Gaussian curvature actually equal to 0, or we can call it is a ruled surface whose Gaussian curvature is equal to 0. But a ruled surface is a surface that can be generated by sweeping a straight line through space, or we can also think of this being a surface made up of a continuous family of straight lines. Now here we take up some common examples of developable surfaces. So there are some examples of developable surfaces that are actually basic developable surfaces. Some examples of these developable surfaces. First of all, suppose if we take a plane. Now plane is itself a developable surface. It is trivially a developable surface. Trivially developable. And second, if we take a cylinder. Now if we compress a cylinder and flatten a cylinder, we will get a rectangle. This flattens into a rectangle. So that means a cylinder is also a developable surface. And similarly, a cone can be developed into a circular sector. Now here actually we know the cone looks like this. So we have the cone like this. If we flatten it, we will get a surface of this form, which is a section of a circle, or we can call it a sector of a circle. Now we take one theorem. This is condition of developability. Suppose we are given a ruler surface, and we know a ruler surface is a surface that can be generated by a straight line by sweeping it across the space. Ruler surface, suppose its equation is given by Cu plus some lambda times du, where this du is the direction vector and Cu is the equation of the curve. Then the condition for developability is, then this is developable. So we can write then the ruler surface R is developable if the scalar triple product, it is the scalar triple product of the direction vector with the derivative, it is del d by del u, and del c by del u, and del c by del u is the partial derivative of the curve with respect to u if this is equal to 0. So that means if the scalar triple product of the direction vector and its derivative with the derivative of the base curve vanishes, then we call the ruler surface as a developable surface, or we can say this is the condition for a ruler surface to be developable. So here we conclude this lecture. In the description of this lecture, we will put one link of the PDF file from a Google Drive that will include some more theorems and the results that are necessary for the examination of differential geometry as far as the entrance exams are concerned.